Okay. Oh, and I need attention. It is so cold in here today. I know it's always cold, but I think because it's wet outside, it makes me feel colder. Boy, we narrowing down on a number of people. I commend you all. I got a few trailing in. Okay, so while we're waiting, y'all want to hear the latest joke? Okay, so what do cows have in their wallets? Moolah. Moolah. Did I do that one already? I didn't do that one yet, huh? No. I forget, like I look up jokes and I don't remember which ones I've said and which ones I haven't. I'm not the best joke teller, if you haven't noticed. Why does a herd of deer always have a lot of money? Because they have a lot of bucks. At least I laugh at them. Nobody else does, but it's okay. No, my aunt sent my son a really good one, and I don't remember what it was now. I have to look when I get home and like take a picture of it with my phone so I remember. She actually sent him a cute one. And he actually kind of giggled, but I think he just giggled because it wasn't from me. I think that's all it was. Okay, wait. Oh, I forgot my chat. What's a pirate's favorite letter? I don't know. What's a pirate's favorite letter? R, right? Do I have to do it with the voice? Yeah. That's good. That's good. I'll have to do that one. You think so, but they tend to get lost at sea. That's cute. That's really cute. I like that one. I'm gonna have to use that one. Jason, I'm stealing it. Be forewarned. That's awesome. Okay, let's see. I'm gonna join in here so I can see my chat on my computer instead of taking up room on the screen. So even if you write in the chat, I'm looking at the chat. I'm just looking at it on a different screen. As if one computer is not enough to have to monitor. Okay. Except, oh, there it is. There it is. Okay. All right, so y'all super excited about our next class period, right? Yeah, I know. Exam. So on Thursday, you do have exam number 2. What topics is exam number 2 going to cover? Chapters 3 and 4. Chapters 3 and 4. So chapter 5, we are starting today, and we'll finish next Tuesday. Okay. All right. As a reminder, I feel like I don't even remember 3 or 4. That's not a good thing. All right. Your attendance is open, so you can go ahead and check in on attendance. And I'm going to talk about a few things real quick, and then we'll do that stuff. So just like with your last exam, you have resources that are going to be available to you. There are a few extra resources. So last time you had the periodic table, the names of the elements, equations, and conversions. Now you will also have polyatomic ions and electronegativity chart. And so if you want to see exactly what you're going to have on the exam, this is a link and you can click on it. And it will take you to exactly what you are going to have on the exam. Okay? Any questions about that? Okay. I think a few people figured out where the Wi-Fi is not good to take an exam. So the dorms, I've heard, are pretty terrible. So you might want to find a computer lab, or some people take it here. That seemed to work out for a lot of people. But there's also a computer lab right over there within spitting distance. Well, depends on how good of a spitter you are, I guess. But pretty close, like down the stairs right there. So just make sure you double check the device that you're going to use, that you have Respondus on it, and that kind of thing. Any questions on like exam stuff?
Is it really like application?
What do you mean?
I was like going over the notes, and it's more like explaining like how to do the stuff over like just new information. There's more like just the in-class problems over like notes.
There'll be some notes, but there's a lot of application. There's a lot of, you know the naming rules to name a molecule. Okay, what's this molecule's name? You know, or here's the name of the molecule. Here's 5 molecules. Which one is it? You know, that sort of thing. Or here's a molecule. What are the functional units inside of it? Right? So you have to know the definition of the functional units, but you have to be able to pick them out on a structure. Yeah? Okay. Is it all multiple choice like last time? Yes, it is all multiple choice like last time. And so it'll open, the exam will open during your normal class period time. Somebody told me I have like the time kind of wonky on it right now, so I'm gonna go in and see. But it will open at, what time do we start? 1:30, and it'll close at 2:50, and it'll be open for 1 hour. Just like last time, exactly like last time. Yeah, absolutely. I'll be here. Every time I have an exam, I'll be right here. So if you want to come and take it in here, because some people had like some technical things happen, and it was really good that they were here and we could fix it. So absolutely, I will be here every single exam So if y'all want to be here, you can. Yeah. Okay. Anybody else? It's a good question. All right. So I thought today I would do quick clicker questions on exam content. Y'all ready? Because you should be studying, right? All right, let's see. So we have 49 people present. If you're not checked in, you need to check in. Please check in. Okay, I think we did this one. Okay, here we go. Full screen. Where's it fit? So 49, that's how many we have. All right, so what is the name of an unbranched hydrocarbon with the formula C5H12? Okay. So when you were looking at this, the first thing you should have looked at was the word unbranched, right? So what does that mean, unbranched? Not that it's not a ring. So C5, 1, 2, 3, 4, 5, right? This is unbranched. This would be branched. Are you going to name them the same? No. Okay, so we know it's unbranched, and we know it has the formula. So do we really have to draw it? We don't really have to draw it. I just wanted to illustrate to you what it looked like. But the other thing that you can do is you can look. It's only got carbons and hydrogens. And if I look at that formula, our molecular formula here, C5H12, right? That fits into this formula. Do you remember this? So what does that tell me I have? If I know that I take my number of carbons and I multiply by 2, what do I have to have? Plus 2. Thank you. Plus 2. 5 times 2 is 10. Right? 2 times 5 is 10. Plus 2 is 12. Thank y'all. So what do you have to have? Like the straight chain, right? And so it's going to be an al what? Alkane, because alkane means all carbon-carbon single bonds, right? So now you just need to remember 5. What does 5 refer to? Pent. Pentane. Okay. All right, so what do we choose? Good. Woohoo. All right. And we said that, but you could draw it out if it helps you. It's fine. All right, so here's another one. It is saturated. It is unbranched, and it has the formula C6H12. Okay, 5 seconds. All right, so now what were our key things here? Unbranched is super important, right? So we don't have any substituents coming off. But what do you notice about the formula this time? It fits CnH2n. So now this one, what does this tell you it is? A cyclo. So you could X out all of these, right? And you're just left with the 2 cyclos. So C6, what is 6? Hexane. The pentagon is 5 sides. So pent is 5. All right, so you can draw it out if you want, but, right? So just be careful that you know that that is cyclo, right? And you could tell that just by looking at the hydrogens. All right. Now, here's something a little more tricky. We've got a minute and a half. How do conformational, I don't know why I did S, conformational and structural isomers differ? How do conformational and structural isomers differ? Okay, 10 seconds. Okay, so tell me about conformational and structural isomers. What's the same between both conformational and structural isomers? They both what? Correct, have had, oh. The same molecular. What's a molecular formula? Kind of like what we saw before, like C5H12, right? That's a molecular formula. So if you counted up the carbons and counted up the hydrogens, in order to be an isomer, you have to have the same number of carbons and you have to have the same number of hydrogens, right? Otherwise, you're not an isomer. Now, how are they different? So we know they're different. So you could look at A and you could cross A out, right? How about B? Conformations represent different rotational forms of a compound. Is that part true? So if I just stand here and rotate my arm, am I still me? Yeah. So that part's right. So if I drew this, is this the same thing as, I'm not a very good artist, so y'all forgive me. How many carbons? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. Is it the same? Are they the same thing? Yes, there's a carbon here, a carbon here, a carbon here, right? We have the same number of carbons. Therefore, we're going to have the same number of hydrogens, right? It's just kind of twisted, but it's the same thing. All right, so structural isomers are different compounds. Is that true? What's the trick to know if it's a structural isomer? What do? We name it differently. So if we are structural isomers, they're going to have different names. Conformational isomers have the same name. So if you have a different name This is how we design the naming system. So that if you have a different name, you are structurally different. We don't want to give two molecules, they're just oriented in a different way, different names. That would get super confusing. I mean, like, you think chemistry is confusing now, it would be torture, right? But the way that we design the naming system, if you follow all the rules, even if it's oriented differently, you're going to get the same name. But if I took my arm and put it on top of my head, right, I would be different. I would be very different. So that would be a structural isomer, right? I still have the same components. I still have two arms, but one's coming out of my head. So I'd be different. All right, so B is correct. So B is correct. What did y'all say? Let's see. So B. Okay, so at least everybody crossed out A. That's really good. Okay. All right, now you need to apply what we just said. So tell me, what's the relationship between these two compounds? How many people did we have? I thought at 1 minute 30. I always forget. Okay, 3 seconds. Okay, so what did you do when you started looking at these molecules? What was the first thing you kind of looked at? The carbons. So let's count the carbons. 1, 2, 3, 4, because I always count my straight chain. Now, this one would be a substituent, right? And which substituent, just for fun? A methyl. Okay. Now, my other carbons, my other molecule, where do I want to start counting? It doesn't actually matter. You could pick any carbon and count because of the way this molecule is. But we could just do this, 1, 2, 3, right? Now, how many substituents do I have? Oh, all right. I have different numbers of substituents. That should be a really big flag for you. So are they the same compound? They can't be the same compound. They can't be, right? There are different numbers of carbons in the main chain, and they have different numbers of substituents. So it can't be. They are different conformations of the same compound. We just said it can't be the same compound, so you have to cross that one out as well. They are different compounds with different formulas. No, so if I really counted all of my carbons, I'd have 5 on the first molecule and 3, 4, 5 on the second molecule. So what's my formula? C5, count up your hydrogens, how much you have? 3, 6, 9, 10, 11, 12. Same thing here, 3, 6, 9, 12. Right? So do they have different formulas? No, they don't. So they must be what? Structural isomers. Yeah? So that's what I'm talking about taking my arm and putting it on my head, right? Same thing. Okay, so what did we say? Oh no, what did we say? B, they're different conformations of the same compound, but we just said they couldn't be the same compound. I'm gonna tell y'all a testing secret. Y'all wanna know a testing secret? It's not really a secret, but it'll help you. If you have two answer choices, right, that have the same thing in them, right? They are the same compound, the same compound. If you can only choose one answer choice, could either of them be correct? No. So you have to cross them both out. You know what I mean? Just kind of like a testing trick. Okay. All right. Oh, we did that. All right. Now this one's a little bit tricky. I'll warn you, this one's a little bit tricky. But go ahead and try and see what you get. So select the correct IUPAC name for this compound. It's a little bit tricky. I hate that every time I move, it makes a sound on the microphone. Like every single time I move. Okay, I'll give you until 1:30. 5 seconds. Okay. So when you were doing this, right? What are we going to name? The ring or the substituents? What's our parent? The ring. So how many carbons in my ring? Well, oh, let me ask you this. Where should I number my carbons? How should I number them? So long as you start at one of the substituents, that's fine. Now, do I want to go up and around, or do I want to go down and around? Whatever makes my substituents at a lesser number, in this case, y'all were saying is down. Very good. 4, 5, 6. So what should I name this? Parent. Well, I want to say cyclo, right? Then what's 6? Okay. Now what? You want to name substituents. Okay, so what are my two substituents? I have a methyl. I have a methyl. So what am I going to say? They're at position what? 1 and position 2, but I'm going to call them dimethyl. I'm sorry, I ran out of room. Okay, is that right? No, why not? What did I forget? I have what? I have this is a benzene ring. That's right, this is a benzene ring. So there are 2 ways that you could actually name this one. You could name this one 1,2-dimethyl benzene. 1,3, y'all. 1,3-dimethyl benzene. Or what's the other way that you could name it? There's a name for double bonds, right? It goes alkane, alkene, alkyne, YNE, right? So you could have named it with the E and E, but was that an option? Not with hex in front. So I'm not going to click this one. I'm not going to make it right or wrong. I just wanted y'all to kind of see. Yeah. So you wanted to go with this one, right? Dimethyl cyclohexane, but what's wrong with this one? It's not this one. I'm not circling it as correct. It's not this one, but why not? Because it has the A and E. And my parent chain has double bonds. And so I have to make sure to say that. Okay, so be careful when you're naming things that you're double checking for double bonds and triple bonds. Okay, my little reminder. Okay. All right, last one. Select the IUPAC name for this compound. Ten seconds. I feel like I should really have like the Alex Trebek music, you know, the Jeopardy. Yeah, you know. Okay, and then I missed my cue. All right, so how many carbons? 2, 3, 4, 5. Okay. So what should my parent chain be named? Pent. I should have a pent. So there's only 2 that have pent in them. Only 2. Is it 2-pentene or trans 2-pentene? Do you remember what trans means? If we draw that dotted line through the double bond, what does trans mean? One thing coming off the carbon will be on one side of the double bond, and then the other will be on the other side, right? So this is trans, right? So trans 2-pentene. What's my other possibility? What else could it have been? If it came up this way, what would it have been? Cis, right? I remember cis and trans? Yeah, yeah. Okay, what do we say? So at least y'all narrowed it down between the 2, C and E. C and E. We just hadn't normally put the name in for cis or trans. We just said, is it cis or is it trans? So I won't count that one against y'all. Okay, so let's switch gears and let's go talk about chapter 5. All right, thermodynamics. This is fun stuff. Full screen. Okay, Jillian. All right, let's see. So I don't need this. Okay, so the next chapter is really talking about how chemical reactions proceed, right? Up until now, we've kind of talked about, we've kind of talked just about what molecules are there with balanced chemical equations, but now we're going to really talk about how those reactions happen. So when vinegar and baking soda are combined, the mixture spontaneously undergoes an endothermic reaction while releasing CO2 gas. Why do kids really like to do this? What do they make with this? The volcanoes, right? All the little kids do the little science experiment and they make the volcano explode. What are they using? Vinegar and baking soda, right? They just dye it with food coloring. So would the test tube feel hot or cold? Do you think this reaction would have a positive or a negative value? Oh, turn off your output. There we go. For delta G, and explain your reasoning. Okay, there's kind of a lot going on right here. Kind of a lot going on. So the question is telling me that it's undergoing an endothermic reaction. Tell me about an endothermic reaction. What does endo mean? Into, right? It's pulling things in. So heat is taken in from the surroundings, right? The ion surroundings to the reaction, right? So if you're holding the test tube and the reaction happens inside of the test tube that's inside of your hands, where is the reaction pulling the heat from? My hands. So if I remove heat from my hands and put it into the reaction, are my hands going to feel hot or cold? My hands are going to feel cold, right? Because the heat that was in my hands is now moving into the reaction. So my hands are that test tube, right? Either way, is going to feel cold. So all the surroundings, anything that's around the reaction, like a thermometer, your hand, the test tube, anything that surrounds the reaction is going to decrease in temperature because heat is being pulled in to the reaction. So would the test tube feel hot or cold? We said it would feel cold. Do you think this reaction would have a positive or negative value for delta G, and explain your reasoning? There's a key phrase inside of the question that tells you your answer. One word. What is that word? What? Spontaneously, right? If something is spontaneous, that means by definition, it has a negative delta G. That's what a negative delta G means. It's the free energy available to do work. It means that this reaction is giving off energy. It's happening so easily. It's spontaneous. You okay on that? All right. Okay. So I left this one for us to do together, just so that we get the terms right. In your own words, define free energy change, or delta G. So delta G is what? I kind of just said it, hint, hint, hint. Well, it means that a reaction is spontaneous. That's true. If it's negative, but we're saying, what is delta G in general? Just the delta G part. The negative part is telling me it's spontaneous. Not the rate. It's not how fast something happens, because like rusting, when something rusts, that's spontaneous. But if you just put your car outside, is your car going to rust right away? No, it's going to take time for that to happen. So it's a very slow reaction, but it's spontaneous. So be careful about saying quick and spontaneous. They're two different things. So delta G is energy. It's the amount of energy it's an amount of energy that is available to do work. So if delta G is negative, it's like this reaction is giving off energy. Okay. So let's see, how does the delta G differ in, ooh, be careful with these terms, exergonic and endergonic reactions. Is that the same thing? Is exergonic and endergonic the same thing as endothermic and exothermic? No, when you think of thermic, what should you think of? Heat, right? When you hear gonic, you should think, I want you to think delta G. Gonic, delta G. Delta G is Gibbs free energy. It's the guy who figured it out. Why they have to do that? It's so mean. Like, I know you're super proud you figured something out. I get it. Please name it after its function or its structure. It's the only two choices you get. So, but just think, thermic is heat, gonic is delta G. All right, so how does the delta G differ in exergonic and endergonic reactions? So if we are exergonic, let's pick that one, EX. Exergonic, tell me about exergonic. Positive or negative delta G? D-E-R. Sorry. If something is exergonic, exergonic means that it's going to happen. You don't have to push it to make it happen. It's going to happen. It's going to be negative. It's the same thing as saying that this reaction is what? Spontaneous. If something is endergonic, then it's going to have a positive delta G. And tell me about being spontaneous. Would you be spontaneous? No, you're going to be non-spontaneous. So if your delta G is positive, you have to put energy in to make it go. That's how much energy you would have to put in to make the reaction happen. And be careful, because look at 5.2. Look at what the book did. It went endergonic, exergonic, and then what did it do? Endothermic and exothermic. They switch back and forth very rapidly. So you need to make sure that you're paying attention to if it's exo what or endo what, right? So be very, very careful about that. All right, let's see. Here we go. Classify the following as exergonic or endergonic reactions. So on a reaction energy diagram, well, I always like to draw it. Let's draw it. The reactants show lower energy than the products. So if you remember on an energy diagram, it's energy on one side of the axis, and then it's time. So as time progresses, tell me what happens to any chemical reaction. Our reactants do what? Turn into products. Okay, so now let's look. The reactants are lower energy than the products. So if my reactants are low and my products are high. So if you watch the video, whenever I talk about energy diagrams, I always talk about riding a bicycle and hills. So if I turn this into a hill, do you want to ride your bike on this hill? I'll give you an option. You can ride your bike on A, or you can ride your bike on B. Which one do you want to do? A or B? I'm riding B, right? B looks really fun to me. I can sit at the top of the hill and then just put my feet up and I can ride a nice little fun ride down, right? Am I putting in a lot of energy to make that happen? No, it's pretty easy, right? How about that first one? How about A? If you're on your bike and you're at the reactants, right? Are you going to have to pedal a lot to get to the products? Oh yeah, you are going to be sweating, right? because you have to pedal to get to the top of that hill. So are you expending a lot of energy to get to the products? Absolutely. So tell me if it's endergonic or exergonic. So remember your definition up here, right? Endergonic or exergonic. Exergonic is spontaneous, endergonic is non-spontaneous. So do you think spontaneously you're going to go in A from the products to the reactants? Are you going to spontaneously climb the hill? No, that's going to be non-spontaneous. So what is non-spontaneous? Endergonic. How about B, where our products are lower in energy than the reactants? Is that going to happen spontaneously? Yeah, right? You get in the right position at the top of that hill, put your feet up, and enjoy the ride. So that would be exergonic. If you always think about these in terms of riding your bike, it makes analyzing them a whole lot easier. Okay. Oh, and gotta go to the next page. All right. Oh yeah, this one. Give the sign of delta G for the reactions in problem 5.4. So let's go back and let's give, maybe, put this out of the way. Like they really just need a little bit more space on this stand. Okay, so tell me about the sign for delta G for A. What's my delta G sign going to be? If it is endergonic. If it is endergonic, it is what? Positive. If it is exergonic, it is negative. Okay? All right, so now I gotta go to the next page. Okay, so delta S. Right, you got G's, you got H's, you got S's in this unit. There's a lot of different symbols to learn in this unit. But if you remember H is heat, H for heat, you got that one, right? And we just talked about delta G, which is free energy. So now let's talk about S. Whenever I hear delta S is entropy. Let me write it. Delta S. Delta S is entropy. I think about the entropy of my son's bedroom. The entropy of my son's bedroom is through the roof. His room is, guess what? A mess. It's always a mess. Always. It doesn't matter what I do, it's always a mess. So I want you to think about entropy like a mess, right? Entropy, another word for entropy is disorder. Let me tell you, his room is disordered. Nicely, his room is disordered. I much prefer my room to be highly ordered, right? Okay, so when we think about chemistry and we think about disorder, the more orientations that you can be in, the more disorder you have. So I want you to think about the different states of matter, a solid, a liquid, and a gas. Tell me about which one is the most disordered. Gas is disordered. Whoa. There you go. Disordered. And then the most ordered then would be, so we go from ordered to disordered. So tell me, what's going to have the highest delta S? Gases or solids? Gas is going to have a high delta S. Solids are going to have a low delta S. right? Okay, so look at our example. Liquid gasoline burning to form carbon dioxide and steam. What am I doing in this one? I have liquid gasoline, and that liquid is turning into, what's carbon dioxide? Gas. What's steam? A gas. So I have a liquid turning into gases. What's happening with my disorder? I'm getting more disordered. If I'm getting more random, right, what's my delta S going to be? I'm going to be positive. Okay? Cleaning up your bedroom. Tell me about cleaning up your bedroom. What I wish my son would go and do. Right? Super disordered. I should write in here, cleaning up Charles's bedroom. Because some people like to keep a clean bedroom. My son is not one of them. What's happening as I clean up Charles's bedroom? That's usually what ends up happening. It's less disordered. So if you say those signs as more and less for delta S, it kind of helps you out a little bit. All right, ooh, this one's fun. A stick of dynamite burning, not burning, exploding. So what's if it's a stick of dynamite, what state of matter? That's a solid, and it's exploding. What does it turn into? Got to be a gas. So tell me what's happening when I go from a solid to a gas. More disorder. So the more extreme that transition, the more explosive the reaction, right? Liquid gasoline burning to form carbon dioxide and steam. We use that to run our cars, right? But a stick of dynamite exploding, we're not going from a liquid to a gas, we're going from straight from a solid to a gas. And so that's going to be a super, super fun, but dangerous experiment. Okay. Classify the following as spontaneous or non-spontaneous process. Walking on a treadmill at the gym. What do we think? Spontaneous or non-spontaneous? We wish it was spontaneous. It is non-spontaneous. Right? Are you putting in work to make that happen? Right? Yes, you are. It doesn't just magically, your legs don't magically move, right? So you have to put energy in, so it is non-spontaneous. A chemical reaction that requires free energy. Very good, y'all, very good. Non-spontaneous. A and B are describing the same thing. A is you as a human being. B is a chemical reaction, but the principle is exactly the same. Okay? All right. Okay, some fun stuff. Now we're going to talk about our application to energy in our daily lives, right? Where do we get energy from? From our food, right? From the things that we eat. And so everything that we consume is not equal, right? We know that when you get a nutritional label, right? What do you get on that nutritional label? It tells you 3 main categories and then it breaks those categories down, right? So you get carbs, you get proteins, and you get fats. And they'll tell you, now you know what it means. When you see that food label and it says fats and it says unsaturated fat, saturated fat, monounsaturated fat, you've seen that. Now you know what that means. So when we look at these food labels, it's important to know what our bodies can use, right? So you're going to eat these 3 major categories, but your body uses them differently. So when we eat proteins, usually our body isn't using that for energy. Usually proteins are broken down and we use them as building blocks, but they do carry energy. Like if you were starving if you were, I don't know, lost in the woods and had nothing to eat for a very long time, you would go into starvation mode and your body would actually break down its own proteins to give you energy, right? So proteins do carry energy, but we just typically use them as building blocks instead of an energy source. So our two main energy sources are carbs and fats. When we look at the biochemical makeup of carbohydrates and fats, they contain different amounts of energy. So fats contain more energy than carbohydrates. So what we can see in our table here, right, is that for every gram of a carbohydrate, I'm going to get 4 calories. That's big C calories, right, not little c. Big C calories of energy. How about fat? I'm going to get 9 calories of energy. So a lot of times when we eat things, we don't really think about everything that's inside of them, right? So if we had a nice breakfast, let's talk about what's in that breakfast, okay? So it doesn't sound so bad. Determine how many calories would be found in a breakfast consisting of 2 eggs, 2 pieces of toast buttered with 1 tablespoon of butter, and 1 6 fluid ounce glass of orange juice. So let's talk about each of our different things that we're having with breakfast, right? We're having eggs. We're gonna have 2 of those. We're gonna have toast. We're gonna have 2 of those. We put some butter on our toast because what good is toast without butter, right? 1 tablespoon. And then we have OJ and whoa. We had how much? 6 fluid ounces, right? 6 fluid ounces. Okay, so can we go in and convert this to energy, to calories? What we have to think about is that each one of these different kinds of foods contain each of our 3 types of energy molecules, right? We have fats, we have carbs, and we have proteins in just about everything. So let's look at each one. Carbs, then we'll do protein, then we'll do fats, okay? So let's do that. All right, so let's look at our eggs first. I should have put this table down below. Eggs. Okay, so now look at our eggs. These numbers are for what? 1 egg. So you'd have to go down and you have to say, okay, I'm going to multiply everything by 2. So 2 times 0.6. So this is how many grams of carbs I have in 2 eggs. So how many grams is that? So this is in grams, this is in grams, this is in grams. I get 1.2, right? Okay, so how about protein? I think y'all gonna have to help me out. Protein, 6.07. Did I say 6? Yeah. 6.07. So what's that? 12, 14, 12.14? Okay, fats, 2 times 5.58. What do we get? 11.16. All right. So guess what? That wasn't all we ate, right? We had some toast too. So y'all call out the numbers to me. How about carbs? How many grams of carbs are in 2 slices of toast? Well, in 1 slice of toast, because we're going to multiply it by 2. 14.1. Okay. That's 28.2. Okay, then protein, not too much protein, huh? 2.4, so that's 4.8. Okay, and then fats. 0.9, so it's 1.8. Okay, now butter. What do we expect to have more of in butter? Carbs, proteins, or fats? Fats. We're gonna have more fats. But okay, so let's do this though. So 1 tablespoon. Let's go back up to our table. What's our serving size for butter? Oh, 1 tablespoon. So do we have to multiply by anything? No. So we can just write it. Okay, so butter, I saw 0.008 carbs. How much protein? And then how many fats? 11.5. So that's a very high percentage of fats, right? And that makes sense. Okay, OJ. I had 6 fluid ounces. Come up, let's see. Oh no. What did they give it to us in? Oh man. What am I going to have to do? Okay, so I need to do some kind of a conversion factor, right? See if I can extend the page. So if I have 6 fluid ounces, I will tell you that in 1 ounce, you have 0.125 cups, I believe. Yeah, 1.25. So how many ounces is that? How many cups is that? Because our ounces cancel. Less than 1. 0.75 cups. Okay, so that's what we need to bring up to the top. So we're going to bring 0.75 and we're going to multiply times our carbs. So how much carbs are in 1 cup? 27. And that gives us what? 20-ish? 20.25. Okay, then we're going to do the same thing, 0.75 times our grams of protein. How much protein? 2 grams. Oh, not too much, right? So that's 1.5. And then 0.75 times 0, right? No fat. Okay, 0. Okay, that was our entire meal. That was everything we ate. We have to worry about everything. So what's our total grams of carbs, total grams of protein, and total grams of fat? How do we do that? All we have to do is add it up. So we have 12 grams of carbs, 28.2 grams in our toast, 0.08 in our butter, and 20.25 in our OJ. So what do we have? $20, $40, $50, $50-ish? 658. Okay, so this is grams of, what was our first column? That was grams of carbs. Then we're going to get protein. Y'all do the math. Protein and fat. So add up the protein next, 1.5, 0.12, 4.8, and 12.14. And then do the same thing for our fat. Okay, so how much protein y'all get? 18.56. All right, and then wait, that was fat or that was protein? Okay, and then fat. Thank you. All right, so is this our final answer? Unfortunately not. Unfortunately not. We were asked how many calories. So what do we have to do now? We have to convert. Now, carbs and proteins, both, for 1 gram of either, it will give you 4 calories, right? So you could just add those up and do one conversion, or you could convert them separately. It doesn't matter. And then the last one, you have to know in 1 gram of fat, we have how much? 9 calories. So we have to go in and convert these. Let me erase this. Okay. So I would do 49.658 grams. And I would convert that and I'd say in 1 gram, and this is carb, 1 gram of carb, I have 4 calories. So y'all do the math. And then 118.56 grams of protein. I know I have 4 calories per gram of protein. And then I have 24.46 grams of fat. And remember, your fat has a different conversion. It is 9 calories per gram of fat. Okay, so what you get for carbs? And this is calories. Okay, anybody got protein? 74.24. I messed up. And that's in calories. And then my very last one, which is fat. You got what? 220.14 calories. Okay, now I want to know all the calories in my whole meal. So I need to add up all of these calories. What do I get? Total. This is total for the meal, right? Okay, so that's a really, really good question. If you come up here and you round for significant figures, because sometimes I hate the way your book does problems, how many significant figures are in the only value that you were given? 1. I think that's terrible. I will try to never ever do that to you. So let's just round to 2 significant figures, because 1 significant figure makes me sad. So how does that round to 2 significant figures? 490 calories. 1 significant figure just irritates me. Like, how could you? How could you? All right. Okay, so switching gears a little bit. We're going to talk about chemical reactions. Now we're going to talk about how quickly something goes, right? Before we remember we said if it was something was spontaneous, it didn't mean that it happened quickly, just that it would happen without having to put an input of energy into it. So now we're going to talk about reactions that will go slowly or reactions that will go quickly, and how we can change that. So describe the activation energy. We're on 5.14. Describe the activation energy for a chemical reaction. Do you remember this little diagram, this energy diagram, right? We went from reactants to products. When I drew this, can I just draw a straight line down? Is that how your energy diagrams look in your book? No. There's this little hump that you have to get over, right? So you start at the products, and then you kind of have to go over this hump. And you can kind of think about that like you're the bike at the top of the hill. If you're balanced, are you going to go anywhere? No. Either you have to pedal just a little bit to get going, right? Or somebody's got to give you a little push. But you need a little bit of an input of energy to make it happen. So that's exactly what this is. Do you see this amount of energy? From where you actually started to the maximum amount of energy that has to go into the system. That is going to be your activation energy. So how does adding a catalyst change that? And then we'll define it. I want to look at 2 reactions. All right, so here's my original reaction, right? If I add a catalyst, how's my curve going to be different? I still have to start at the beginning. I I still have to start here, and I still have to end here. How can, a catalyst is supposed to make a reaction easier. What's the one thing that I can change? The amount of energy needed to start it. So that activation energy. So if I lower that activation energy, now look how tiny that activation energy is, right? If I were a good artist, you would really be able to see it, but I'm not. But you can see how that activation energy has gotten smaller, right? That's what a catalyst can do for you. The catalyst will decrease the activation energy. So how does adding a catalyst increase the rate of a chemical reaction? It decreases the activation energy. So what is the activation energy? How can we define that? It's that little bit of energy that you need to get going. So it's the minimum amount of energy, right? Required for what? For the reaction, to transition from reactants to products, to overcome the energy barrier, however you want to phrase that, right? To transition from reactants to products. You could say to overcome, these are just two different possibilities. Overcome the energy barrier, right? Because when you're sitting at the top of the hill, there's an energy barrier between you and getting to the bottom of the hill. It's not a very big one, but it's still there, right? And so a catalyst will change that for you. All right, so if I were to look at the two diagrams that I just drew, do you think the diagrams that I just drew would be for a fast reaction or a slow reaction? This is like the wind in your hair, right? Blowing you back. This is a fast reaction. If I were to draw a slow reaction, right? Then I would draw something that looks like this, right? Where I had to put a lot of energy in order to get there. Trust me, if you had the same distance to cover, same distance, and one person was going up the hill and the other person was going down the hill, who's going to get to their destination more quickly? The person climbing up the hill or the person just flying down? The person just having fun, right? Going down. So a slow chemical reaction has, what do you think? What kind of activation energy? High or low? It has very high activation energy. So tell me, where's the activation energy in this new energy diagram that I just drew? It's the minimum amount of energy required to transition from our reactants to our products. I'm going to start here. Where do I have to go to reach my activation energy? Oh my God, all the way to the top, right? That's a huge activation energy. Does that make sense? Why it's so high? Because you're starting out at a reactant that's a very low energy and you're trying to get to a product that's a high energy. How are you going to do that? You're going to put in a lot of energy. Just think about like the potential energy of somebody sitting at the bottom of the hill. Do they have a lot of potential energy? No, they don't. But if you put a lot of energy into them, they will climb that hill and they'll sit at the top. Now, what kind of potential energy do they have? A lot of potential energy. So that's like the product. Now we're sitting at the top. We've worked hard, we've sweated, right? But we've reached our product. But we had to put a lot of activation energy in to get there. All right. So another word for a catalyst is a is an enzyme, So in an enzyme, there are a couple of different kinds of enzymes. Some enzymes can just be like I think of them like as a serving tray, right? They just kind of sit there and they're a surface for my reactants to get together on, right? Then there are some catalysts who actually have these sites that bind to reactant molecules. They actually kind of reach out and grab them and then orient them and kind of stick them together. So if I have an enzyme that's able to reach out and grab them and stick them together, what do we call the location where they call it catalysis, happens? It's very specific for each individual reactant. The active site. Active site. And that's how almost all of the enzymes work inside of our bodies. They have active sites and they fit particular things. Okay, but catalysts aren't the only things that can change the rate of a reaction. There are a couple of other things. So let's look at a couple of scenarios and see what happens. Adding a metal surface for two reactants to locate each other. This is kind of like that serving tray, right? You're providing a surface for those reactant molecules to hang out and get to know each other and have a reaction, right? So what's going to happen? Are we going to increase or decrease the rate of our reaction? We're going to increase it because we're giving them a surface so that they can interact on. Decrease the amount of one of the reactants. We're going to decrease. Because what is really a reaction? It's a collision. So sometimes I like to think about chemistry as cars on the road, right? So if we're at rush hour, tell me about rush hour. A few cars or a lot of cars? A lot, but I'm not really thinking Thibodeau. we gotta think like New Orleans, right? So a lot of cars at rush hour. What tends to happen at rush hour? People get into wrecks. Why? For two reasons. They're going too fast and there are lots of cars on the road, right? Same thing is true about chemical reactions. When molecules go really fast, they collide more frequently. What is molecules going fast? What do we define that as in chemistry? If molecules go fast, they're hot, right? If molecules go slow, they're cold. So if we slow down the molecules, they're less likely to bump into one another. They're less likely to wreck. And so you slow down a reaction. This is why we put our food in the refrigerator, right? So if you had the same like leftovers and you left one out on the counter and you put one in the fridge, what would happen? The one out on the counter is going to start growing, right? But the one in the fridge, it's going to take a whole lot longer. And why? Because all the microorganisms that are living inside of that leftover food, because there's some, it's not perfectly sterile, everything inside of them is slowed down. All their chemical reactions inside of their cells are slowed down. And so that's why we put food in the refrigerator, because it slows down their chemistry, their reactions. Okay, and that was like so off on a side note, but okay, so what if we're in rush hour in New Orleans, right? And we snap our fingers and half the number of cars are gone. What's gonna happen to our accident rate? It's gonna drop, right? So that's exactly what we're saying. We decrease the amount of one of the reactants, and our rate's gonna go down. How about we, in C, caramelize onions on a medium-high SO setting versus a low setting? It's going to increase our rate. Why? Because we increase the temperature. If we increase the temperature, we increase collisions. It is really collisions that tell you your rate. Okay. All right. Okay, section 3 We only have like 5 minutes. So what I'm gonna do is I'm gonna call it for today, but not tomorrow, Thursday. It is virtual. So if you want to be here, I will be here. If you would prefer to be in a computer lab where you are hardwired to the internet, that's cool too. But it is an exam on Thursday. On next Tuesday, I'm going to be finishing chapter 5. So you need to make sure that before you walk in the door on Tuesday, that you have all of chapter 5 watched, okay? I'm gonna post the rest of the lectures, I think like tonight sometime. So if you have any questions, feel free to ask. Good luck studying. All right, anybody on the Zoom need anything? Y'all have any questions? Okay, I guess that's it. Y'all are good. So I'm gonna go ahead and end the meeting.